In this lecture, we are going to learn about quicksort. As the name suggests, so this is a very fast sorting algorithm in which you get a average performance of theta of n log n. Okay, and it does in place partitioning. So in place partitioning, and it's quite fast. So it gives result in theta of n log of n time, where n is number of items to be sorted. So that's why we have shown it with a leopard. Okay, so quicksort, let's see what it does. So it's based on a very famous paradigm known as divide and conquer. Okay, so it's based on divide and conquer, which means that we divide the main problem into some smaller sub problems which are of similar type but whose input size is smaller. Okay, so let's define it. So we have an array A. Okay, so A1 to n, there are n elements in it and it's indexed from 1 till n, and what we need to do is in divide and conquer, we first divide the problem into smaller sub problems and then solve those sub problems, and finally we combine the smaller results of smaller sub problems. So here, what is the divide part? So this is the divide part. We partition the array AP to R, which means the array in starting index is P, last index end index is R. So we divide this array into two sub arrays. Okay, one is from AP to Q minus 1 and another is AQ plus 1 to R. Okay, so we somehow divide the array into two parts. Okay, and they are not equal. Okay, so but they are something like, okay, so we have a qth element and this is AP to Q minus 1 and this is AQ plus 1 to R. Okay, so this side, and what we do, so all the elements on this side, so this is all less than equal to this element x. Okay, so this is less than equal to x and this is greater than equal to x. Okay, so we do the partition so that all the elements to the left of qth index are less than equal to AQ and all the elements to the right of qth element are greater than equal to A of Q. Okay, so this is the partitioning algorithm. So it will be, for example, we have, so let's say we have some number 3, 7, 1, 2, 8, 10 and 4. Okay, so there, and let's say we have one more 5. So we have total of how many? 8 elements. And if we say that we want to partition this array in two parts, and what we have is that we take this last element as the pivot element. Okay, so we have this element as the pivot element. So one solution to partitioning is, so we see that, okay, 3, 1, 2, 4 are less than 5, and then 7, 8, 10 are greater than 5, and now we include this 5 here. So we see that this part, everything is smaller than 5, and this part, everything is greater than 5. Okay, so, and one more observation is that this is not sorted. So not sorted. So partitioning doesn't mean that okay, this side is sorted. So 3, 1, 2, 4 is not sorted, even though 7, 8 and 10 is sorted. Okay, the only criteria is in the left sub array everything should be less than equal to this element, and on the right hand side everything should be greater than equal to this pivot element. Okay, so this is partitioning, one solution. Other solution can be 3, 4, 2, 1, 5 and then 10, 8, 7. This is also a valid partitioning. So only criteria is that I should get in the left every number should be less than that pivot element, and on the right everything should be greater than the pivot element. Okay, but now we see that there is a beautiful result. Okay, so what is the sorted form of this? So we have 1, then 2, 3, then 4, 5, then 7, 8 and 10. Okay, so this is the sorted array. And what are the indices? So this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now just try to find the index of the pivot element which was 5 after partitioning and after sorting. Okay, so after partitioning in both the cases the index is 1, 2, 3, 4 and 5, and here it is 1, 2, 3, 4 and 5. So the index of the pivot element for us is 5 in the partitioned array. It was 8 in the given array, it was 5 in the partitioned array, and it is 5 even in the sorted array. Okay, so this is one observation. So we observe that the index of the pivot element is same in the sorted array and in the partitioned array, and it is not guaranteed to be same for others. Let's say we take the index of this 8. So 8 is here, so 5, 6, 7. So 8 here is in the 7th index, and here also it's in 7th index. So lucky, so this is at the same place. But let's say we take 2. Okay, so 2 in this partition it is in the 3rd index, here it is in the 2nd index. In this partition it is in the 3rd index again. Okay, so they are not matching. So 7 also. Okay, let's see for 10. So 10 here is in the 6th index, and here it is in the 8th index. So only we can guarantee that in the sorted array and in the partition array the index of the pivot element will be the same. So this is point to be noted. Okay, so the index of pivot is same in the sorted array and in the partitioned array. So now we have got, after divide part, we have got that okay, we get an array where we fix the position of the pivot element, so it goes to its correct position. Okay, and then what we do, we also now call the quick sort on the left subarray and the right subarray so that we can sort them. Okay, so let's see. So conquer part is sort the two subarrays a p comma q minus 1 and a q plus 1 to r. So we sort these two arrays again recursively, and combine means because now all the subarrays are sorted, so no need of combining because they give the sorted array itself. So quick sort, what we do, p is the left index, r is the right index. If p is less than r, then we go on doing the work. If p is greater than equal to r, it means that okay, so p is equal to r, it means that okay, I have only one element left, greater than r cannot happen. Okay, so q is what? So we find the q is equal to partition a p comma r. So this what it does, so array we pass the left index and the right index of the array which we want to partition. Okay, so Q, this gives us the index of the pivot element in A, P, R. Okay, so this gives us the index of the AR in the sorted array. Okay, and it fixes its position. Then what we do, we call recursive calls for smaller sub problems. Quick sort A, P, Q minus 1. So it's something like this is the array. So this is P and this is R, this is P plus 1, P plus 2, somewhere there is qth element, this is R minus 1. So what finally this does is that, okay, so we have in this, after this call of partition, we have A of R here, which is at its final position, qth position. Everything here is greater than equal to A of Q. Everything here is less than A of Q. Okay, and this AQ is basically AR. Okay, that was there in before the partition was called. And then what we do the same procedure for A, P to Q minus 1, which means now we are calling quicksort on this sub array and this sub array on the right. Okay, and we already got this AQ, which is in its final position in the sorted array. So now how we call this function? So this small piece of code will do the trick for you. So now initial call will be quicksort A, array we pass, and starting left position is 1 and length of A is the number of elements in it. Okay, so now what is the partitioning procedure for an array? Okay, so partition A, P, R. So let's say that, okay, we have the pivot we decide and it's A of R, which is the rightmost element. Then what we do is I is P minus 1 initially. Okay, so for J is equal to P and J is less than equal to R minus 1. So what we do, so for J from P to R minus 1, we check that, okay, if AJ is less than pivot, then we increment I. So let's see it first with some example that will make it more clear. Okay, so we will try with this example. So we have some variable, this is 1 2 3 4 5 6 7 8. So these are the indices. So now initial I is 0. Okay, and J starts from P. Okay, so J starts here from P and it goes till R minus 1. Okay, so it goes till R minus 1, which is 7. And what it does, so what it does is it checks that, okay, if AJ is less than the pivot element, then we increment I. Okay, and swap AI and AJ. Okay, so let's see what this does. So I is 0 initially, we start from J is equal to 1, and we want to partition such that on the left side everything is less than A of P, which is, so here what happens, P is 1 and R is 4. Okay, so R is 8, basically we are doing the indices. So now what happens, J goes from J is equal to 1 to R minus 1, which is still 7th index. So if AJ, okay, if AJ is less than equal to, so X is equal to here, or the pivot is equal to A of R, okay, which is now 4 for us. So if AJ is less than 4, the pivot element is this one. So if AJ is less than 4, what we do? We do I is I plus 1 and we swap AI and AJ. Okay, so what happens, we have J here. Okay, so let's see what happens. So if we check the code here, So if aj is less than pivot, then we do I is I plus 1 and swap ai and aj. Okay, so we swap ai, I is now becoming I plus 1, so I becomes 1, and j is also 1. We swap ai and aj, but both are indices 1, so nothing gets swapped. Then what happens? We go to j is becomes 2, and now we come to 8. So now aj is not less than the pivot element, so j is again incremented, it goes to 7, and now again a of 3 is not less than the pivot 4, so it moves further. Now j comes to 4, where a of 4 is 1. So j comes here, and now we see what? So we now see that a of j, which is a of 4, is less than pivot element, which is 4. And our I is now at 1. Okay, so I is at this place and j is here. Okay, so what we do now? So if we see the code here, so if aj is less than the pivot element, so we do I is I plus 1, and we swap ai and aj. So let's see. So j is this, I is this, so I becomes, now here it goes, and what happens is we swap 8 and 1. So it becomes 2, 1, 7, 8, 3, 5, 6, 4. Okay, so now what happens? J is here itself, I is here, and now what happens is that we swap 1 and 8. Okay, so this basically tells why are we swapping. So we are swapping because now 8 and 7 was a window of numbers which were larger than the pivot element, but now as 1 is less than 8, so we swap here so that the smaller element goes to the left, okay, and larger number comes to the right. So now it has like this, and I is here, so we see that we get a window which is this one of numbers which is greater than equal to the pivot. Okay, then what we do again, next one, so j now becomes 5, it goes here, and so what we do, if a of j is less than equal to pivot, and it is so we again swap aj and a of I plus 1. So we make I is equal to I plus 1, I comes here, and what happens? So 2, 1, 3, 8, 7, and we have the window like this. Okay, so we have the window here, so 7, 8, 7 comes here, and 5, 6, 4. Okay, so now we have 2, 1, 3, 2, 1, 3, so this is correct, and so we have something like 1, 2, 1, 3, and now our j comes here. Okay, so let's see. Now what we do, j is here and I comes here. So what we need to do, again we check if aj is less than equal to the pivot element, which is not the case. So what happens now is, now this also comes under the window of greater elements. So this now becomes larger, the window of numbers greater than equal to x, and again when we check j, so j is now again a of j, which becomes j is 7. So for j is equal to 7, aj which is 6 is greater than the pivot element, so this window becomes still larger, and it has now 8, 7, 5, 6 in it. Okay, so we have this window now of larger elements, and here we have a part of smaller elements. Okay, so and finally the for loop ends. So I is here, and what is the case? So we have I which is at 3, and here we have, so now we swap a of I plus 1 comma a of r. Okay, So now let's see what happens. So 2, 1, 3 and then 4, 7, 5, 6 and 8. Okay, so this pivot comes to its correct position, which is 4, and 7, 5, 6, 8 is on the right, and 2, 1, 3 is on the left. Okay, so now we see that, okay, in this one we have the pivot element which is fixed, and so this way we have a first partitioning. So now what we do, we call quick sort, so A 1, 3 and quick sort A 5, 8. Okay, so now we have very small arrays. So here again, if you see, so we will be running partition. So now in this part, partitioning algorithm will again run. So for that, the algorithm is, if we see here, so what was the quick sort? So after partitioning, we run quick sort in the left subarray and on the right subarray. Okay, so that's what happens. And 2, 1, 3 is here. So here again partitioning runs. This is the pivot element. So 2 and 1 are both smaller, so this remains like this. And after this, this number is also set at this position. And here 2 and 1 for this subarray, again quick sort is called with this as the pivot element. So now it will be sorted and we will have 1, 2 and then 3, 4. Then we have the right subarray for which the partitioning, the quick sort is called. Here again we partition. So this will be the partitioning pivot element, and all numbers are again here, so lesser than 8. Okay, so this is now also at fixed position. So now we call quick sort on the left subarray, which is 7, 5 and 6. So in this 6 is the pivot element now. So what happens is, so we will get 6 here, 7 and 5. So now we see that, okay, this is at the sorted position. It will call quick sort for the left subarray, which is this, and right subarray this. So these are all just of single element arrays. So these are already sorted. So we get a sorted array. Okay. So this was about quick sort. So now we will try to analyze the algorithm. So first we try to see the worst case. So that's very important, because worst case gives you the idea about the what is the maximum it will take to run this algorithm. And the worst case will happen when the partitioning gives you very like skewed partitioning. So one side it is all the n-1 elements are on the one side, and on the other side there is no element. Okay, and that happened also with this one. Like, okay, here if we, for this subarray, so if 8 was the pivot element, everything was smaller than this. So in the size n is equal to 4 here. So one subarray was of size 3, other was of size 0. Okay, so this way we see that, okay, this partitioning, if it happens, so Tn is Tn minus 1 plus T of 0 plus theta n. And why theta n? Because in the partitioning algorithm is theta of n, because we ran a for loop from j is equal to 1 to, or from p to r minus 1. Okay, so that was theta of n. So this is Tn minus 1 plus c of n. And then what happens? Tn minus 1 can again be written as T of n minus 2 plus c of n minus 1. So this whole expression becomes T of n minus 2 plus Cn plus c of n minus 1. Now T of n minus 2 can be written as T of n minus 3 plus theta n, which is c of n minus, so Tn is Tn minus 1. Okay, so this can be written as T of n minus 2 is T of n minus 3 plus c of n minus 2. Okay, so this way if we keep on writing, we see that it will become a theta of n square, because 1 plus 2 plus 3 till n. So the sum of digits is, first and natural number is n plus 1 by 2. This is theta of n square. Okay, so that's why we, in the worst case it is theta of n square, and in the best case what happens, we get a partitioning where both sides are of equal size. So this is the case, Tn is less than equal to T of n by 2 plus theta n. Theta n will be always there because partitioning takes theta n running time. So by Master's theorem, if we solve this, so it will be theta of n log n. Okay. So the other one is that, okay, if it's not so balanced, then Tn is, let's say that the ratio it divides it into is 9:1. Okay. Then Tn is T of 9n by 10 plus Tn by 10 plus Cn. And if again we solve this recurrence, it will be theta of n log n. Okay. So we see that in average case, there is much more mathematical details in finding the average case, but we will find that average case is theta of n log n for quick sort. Okay. And this was about quick sort. I hope you understand this algorithm. And if you like this video, please share it among your friends.